Okay, so now we're on to polar lines, and this one starts out very similar to the beginning of the polar circles, because with the beginning of the polar circles you had an equation where it was just r equals with no theta. This equation is just the opposite, which is you have theta equals with no r. And so what that's telling you is that, for example, no matter what your r value is, your angle is always going to be 135 degrees. And so what that means is you could make up r to be anything. It could be positive 2, it could be negative 4. It wouldn't matter what r is as long as you are traveling towards or away from 135 degrees. So if I plotted those 2 points, I could go 2 units towards 135, which would be right out there. I could go 4 units away, 1, 2, 3, 4 units away from 135. I could go 5 units away from it. I could go 0 units away from it. I could go 5 units towards it. It wouldn't matter what I made r to be as long as I'm traveling along that line. And so what it generates is this set of points, sorry, it's not my best line, that are all traveling towards or away from a 135 degree angle of direction. So then to transform it into a Cartesian equation that agrees with that line, what you would do is you would use that formula from the beginning of the unit where tangent of theta was equal to y over x. And for this line, all of the angles were 135 degrees. And so I substitute the angle into that equation. And tangent of 135 degrees is negative 1. And so what we have is this. And remember that, once again, I'm going to keep reminding you guys, this is a proportion, so that x is just going to multiply up straight across. And so I have negative x is equal to y. There's my Cartesian equation. And so that's the slope-intercept form of a line. It's a line with a slope of negative 1 and a y-intercept of 0. So then the next type of equation is, remember that how this compares to the circle. The circle was r equals a constant times sine or times cosine. Now this is a constant divided by sine. And with this particular polar, it's incredibly beneficial if you learn to recognize it right away in its polar form, because as soon as you know that it's a polar line, how many points do you need to graph a line? 2, right? So that means that you would not have to do the complete table of values. You would only have to do 2 of those. Because watch what's going to happen if you don't recognize that it's a line. You're going to plug in all of these angles. You're going to have 3 over sine of 0 degrees, which is 3 over 0, which is undefined. So that'll give you no point to plot. Then you would do 3 over sine of 30 degrees. And of course sine of 30 degrees is 1/2, and dividing by 1/2 is the same thing as multiplying by 2, so you would get an answer of 6. And so you could plot that point, 1, 2, 3, 4, 5, 6, right there. Then you would go on to 60 degrees. Sine of 60 degrees, of course, is not as neat, and so you would have 3 over the square root of 3 over 2, which would end up becoming 2 square root of 3, and then you would have to decimal approximate the location of that to be about 3.5. So 1, 2, 3.5, somewhere right around there. And then you would do sine of 90, which is 3 over 1, so you would get 3 at 90. And so you would spend all this time plotting all these points, and hopefully after a few of them you would begin to recognize that they're all lying on a line, and so you wouldn't need to continue. If you did continue, you would end up getting the same answers but for the symmetric angles. And so you would spend all this time generating points when you only needed 2. So if you learn to recognize, especially from the summary page is incredibly helpful, that this is a polar line, then you only need 2 points to draw that line. And so what you would do is you would look at the table and you would find only the angles that worked out with nice pretty answers. So you would try the 30 and the 90, because sine is pretty when you're doing sine of 30 degrees and sine of 90 degrees. So that way you would avoid doing all of these undefines and the decimals. Okay? So now we can convert this into Cartesian to confirm that we should have had a horizontal line. And so remember how we did this on the polar coordinate notes. Remember, you've got options. You could take this sign right here and you could substitute y over r for it, but then you're dividing by a fraction. So what I'm going to do first instead is I'm going to multiply this up. And I have r sine of theta is equal to 3. And in the polar coordinate notes at the beginning of the unit, you were told that the formula to calculate y was r sine of theta. And so that means that that whole left side gets replaced with y, and it's equal to 3. And so sure enough, you have the equation for a horizontal line, slope of 0, y-intercept of 3. So remember that the next one is actually easier because it's already been rearranged for us. So we could just substitute, but we do want to identify as much as we can from it before we do that. So, okay, this has cosine attached to it, so it means that it's going to be related to the x's. So instead of a horizontal line, it's a vertical line. And that sounds weird to say that it's related to the x's, so it's a vertical line, but remember that vertical equations are written as x equals something. And it's going to have a positive 6 value, so it's going to have an x-intercept that's equal to 6, and it's going to be vertical, so it's going to have an undefined slope. And so remember from the beginning of the unit again that the formula to calculate x was always to do r cosine of theta, so that's what this is all going to get substituted for. And sure enough, you have the equation of a vertical line at 6. So now we get to the messy lines, and this is incredibly beneficial to know this is going to be a line. These are the only equations that are this messy. So that means that if you recognize that it's a line, you know you want to only choose numbers that are going to work out nice and pretty in your table. And so you're only going to choose 0 and 90. Even if you don't recognize that it's a line, once again, you really should never need to make it past those first 4. But these are going to be, these two right here are going to be really ugly, because if I try to substitute those, I'm going to have, I don't have enough room to write, so I'm going to erase in just a sec. I'm going to have cosine of 30, which is going to be square root of 3 over 2, minus sine of 30, which is 1/2, all in the denominator. So I would have to simplify that denominator a lot just to divide it into 3. So you really want to avoid doing that. So I recognize that this is a line. Make flashcards, do whatever you need to do. These are going to be the only 2 rows that I do, and that's because when I do these two, I'm going to cross this off to give myself room, I have cosine of 0 degrees minus sine of 0 degrees. And so I have cosine of 0 is 1 minus 0, which is just 3 over 1. So I end up with 3 at 0 degrees. And so I put that one 1, 2, 3 units out towards 0 degrees. There's my first point. And then I do my next point, which is 90 degrees, right here. And so then I have 3 over cosine of 90 degrees minus sine of 90 degrees. So I have 3 over 0 minus 1. And so I get negative 3 at 90 degrees. And so that means that I'm going to go 3 units away from 90 degrees. So 1, 2, 3 units down away from 90 degrees. There's my 2 points. And that's all I need because I know that it's a line going into it. And so there's my line. So please make yourself flashcards or something so that you can begin recognizing. Otherwise you're going to have some really ugly number crunching here in the middle to do on that table. And then even if you did the ugly number crunching, you would still avoid doing the 120s and 150s because of how messy that denominator is. So to summarize your lines, we have 4 different varieties. So we have r sine of theta is equal to a constant, and remember that the way it was given to us before is that it was r was equal to the constant divided by sine. So it can also be given to you in that arrangement form, and what you ended up with is you ended up with a horizontal line at whatever that constant was. The reverse of that, of course, was that we had r cosine theta was equal to a constant, so that could have also been given to us as r equals a constant divided by cosine of theta, and that will give you a vertical line at x equals whatever that constant is. The first line that we graphed was where theta was equal to a constant, so r didn't matter as long as you were traveling towards or away from that angle. And so what we have is we have a line through the pole at that point. And then the messiest one was the oblique line. And it's got to be an oblique line not through the pole, because technically this line right here was also oblique, but it doesn't have to be. It could be oblique, it could be vertical, it could be horizontal. It's the only one that goes through the pole. Okay? So this is going to be an angled line not through the pole, not through the origin. And there's a relationship between the A, the B, and the C value. And so I'm going to do that at the tail end of this, so you can ignore it if you want to. It's very handy. But there is a relationship between those, and you're usually best discovering it when you convert one of these equations into its Cartesian form. So we're going to actually try that, and that might help you understand the relationship. So here's this last situation. I do really quick want to point out that down here in this denominator, I'm going to change colors back to red. Down here in this denominator, I want you to notice that the trig functions need to go alphabetically, because otherwise you're going to get your coefficients mixed up. So b is always the number in front of cosine, and c is always the number in front of sine, because the trig functions are listed alphabetically in the denominator. So what I've got here is I've got an equation where my a value, my numerator, is 3. My b value, the coefficient in front of the cosine, is 2. And then my c value is 1. Okay? And so I'm going to use those to figure out how did that relate to my slope and y-intercept once I've converted to Cartesian form. So we know that because of the fact that this is the only equation that's this messy in the entire unit, that this is going to be our oblique line. They're the only ones that have this type of equation with the messy denominators. And it's going to be not through the pole. And so you could do some quick theoretical mental math where you plug in your 0 and your 90 and figure out a couple of the points on there. When you plug in 0 degrees, for example, in this, which is essentially the same thing as calculating your x-intercept, and you plug it in, what you get is 3/2. And then when you plug in 90, which is essentially calculating your y-intercept, you end up with +3. And so that gives you 2 points on the line. So that's actually quite a bit of information about that line without ever converting to Cartesian form. So now I'm going to convert to Cartesian form to confirm it and figure out the relationship between A, B, and C and my normal slope and y-intercept information about my line. So I had r was equal to 3/2 cosine theta plus sine theta And just like with the polar coordinate notes, I'm going to take that entire denominator and multiply it up to the other side. And then I'm going to distribute r through. So I would have 2 r cosine plus r sine is equal to 3. And of course r cosine is the formula for x, and r sine is the formula for y. So there's my standard form. I could be done, but remember I want to determine the relationship between a, b, and c and my slope and y-intercept. So I am going to put it in slope-intercept form. So there's my slope-intercept form. I mean, either of these equations would have been perfectly acceptable as an answer for Cartesian form, but now we can determine the relationship between some of these things. So I want you to look at the slope. The slope was -2 in this case. And so I want you to figure out where that -2 came from. So if you look at the -2 and the numbers up here, then, and you think about what you did when you were doing your rearranging, hopefully what you figured out is that that 2 was what was attached to the cosine. That was your b value. And it multiplied up, but then eventually it ended up having to be subtracted over. So what we had done is we had taken the opposite of that b value, and then we had taken that c value, whatever was in front of sine. In this case, this was just an invisible 1. If there had been something else there, we would have had to divide it to move it over, to put this in slope-intercept form. And so that's what ended up happening, is just that c was equal to 1. And so what that means is that if you know by looking that this is a, this is b, and this invisible 1 right here is c, you can do your characteristics of your line, and you can know your slope and y-intercept without doing the table or any polar calculating. And so now what's the relationship between the y-intercept? And so if you look at how this y-intercept came about, our y-intercept was 3, and our numerator was 3, and that's because when I took my denominator up, the 3 was left over here by itself, and once again, whatever number was here in front of this would have had to have been divided to move it over here, but ours was just an invisible 1. And so what that means is that whatever that a value is up in your numerator, the only number that's going to impact it is the number that would have been in front of this, that would have multiplied up to the left and then ended up having to divide back down to the right. And so, you know, y-intercept is whatever a over c is. Okay, so that's handy information that can save you calculating, number crunching, all kinds of stuff. You can look at this equation and you can go, oh, 3 over 1, my y-intercept is going to be 3. And then take the opposite of that number and put it over that number, and you'll know what your slope is, and so you can plot another point on there very easily and be done drawing your line. So that's it for polar lines, and we'll move on to our final 3 polar shapes in a few days.